again. My name is Chris Mullins, and I'm with CapEx Sales. Delighted to be joined by Jeff McBee. Jeff's been with Cincinnati Test Systems, what, almost 30 years now? Something like that, Jeff?
Yeah, it's been 30 years as of July.
Fantastic, man. Congratulations. That's awesome. I can remember back in 2009, I went to, I wasn't even an employee with CapEx. I was looking to join the team with Russ. I came down to Charlotte to a trade show, and you were the first person from Cincinnati Test Systems I remember meeting. And we've been fast friends ever since. So Jeff's held many roles at CTS, and from service manager to fast forward to today, where you're business development for our leak location products. Anything else on your plate these days, Jeff?
My main responsibility is HVAC and appliance, but certainly I know everything there is to know just about when it comes to leak testing for just about every industry out there. So
awesome. Well, very good. Well, why don't you take us through leak test technologies, and I may ask a few questions along the way. I'll let you lead. Sure.
We've got about 30 slides here. So this is what the topics of the session is going to be is we're going to discuss how each one of these technologies work, what their sensitivity levels are, and the applications for each. So just kind of starting off, you can see that mass flow is the least sensitive, followed by differential flow, pressure decay, and then differential pressure decay, and then dunk tank. And then you've got accumulation, atmospheric sniffing, carrier gas. Then you've got the CTS, patented purging clamshell, and hard vacuum. And the ones we're going to kind of highlight here today are the accumulation, sniffer, and purging clamshell and hard vacuum. So this kind of gives you a visual when we talk about the leak rates, bubbles underwater versus the actual leaks, and you can see bubbles versus leak rate. That's pretty interesting. So the first one we're going to cover is the nitrogen purge technology, or I'm sorry, leak location. And what's leak location good for? What are we trying to find with leak location? Mainly water ingress, water leaks, coolant leaks, hydraulic fluid leaks, oil and transmission fluid leaks, and natural gas. So this is all things that you can use an open air sniffer with, sniffing around different joints, different areas of the part, and typically these are the types of leaks that you're looking for. And there on the right, that's a picture of a leak location cart. So kind of the principle of operation of a leak location. First, we're going to evacuate the part, and we're going to evacuate the part. So when we backfill with the forming gas or helium, which is the next step, we'll be able to find that leak quickly, because if not, we're just pushing the trace gas in on over top of the air that's already present in the part. And so therefore, before you start actually sensing any tracer gas coming out that hole that might be present in your part, you're going to have to displace all the air that's in there first. But if you pull vacuum, you're getting rid of all the air. Then when you backfill, you're able to pick that leak up rather quickly. And with that, once your part is charged, you're going to use the sniffer one, like I said, to go around different joints, different weld joints, different areas of the part that you're interested in trying to find a leak on. The sensitivity range of leak location with good background control is down to 1 × 10⁻⁵ cc's per second. And that's based on the wand movement. So if the operator gets too happy and moves the wand around too quick, about the best you can hope to pick up is gross leaks. But if they do, let's say with a 300 cc per minute flow, if you go 3 inches a second, Or if you're using a high flow sniffer, which is 3,000 cc's a minute, I'm sorry, then you'll be able to pick up something. You can probably move at least 6 inches a second.
I think one of the other points here for folks that aren't familiar with sniffers, sniffer technology and sniffer wands is that, I mean, and maybe you can explain a little better than I can how the actual wand behaves as you're approaching a leak.
Yeah, when you're actually approaching a leak, you'll start to hear the audible on the sniffer increase. And then when you go over the threshold that you've got set, then it will go off, and then the light on the front of the tracer mate and the display and the wand will all turn red. When you move away from the leak goes away, it goes back to the red light will drop out and the audible will drop out. And when you go back in to verify that's where the leak is at, all of a sudden all the displays will turn red again, and you'll also get the audible once again.
Yeah, and these wands have become very nice. They have a LCD display, and they vibrate as well. So really gives the operator some good feedback.
Yeah, you can see the picture of the wand right there. I don't know if you can see my mouse or not.
Yep, I sure do.
Yeah, so that's the one right there. You've got a little display there that will turn red. The display here will turn red, and you've got LEDs above and below the tracer mate display that will also turn red. So all those will turn red simultaneous to let you know, along with an audible, to let you know you've got a leak. So there's no way an operator should ever miss a leak if they come across one, because it's going to give them every sound and light under the sun to be able to pick that leak up. So it's very apparent there's a leak when you go across one. And to verify that you have a leak, you go in and find the leak, and then you back away and you go back in just to make sure it's not a ghost signal, make sure it's just not background that's setting the leak detector off. Some of the applications for, and so we're only going to cover each one of these as kind of a 90,000 foot view. We're not going to go into it in great detail, but just enough that you can kind of see the difference between each trace gas technology. Some of the applications inside there is inside the using a leak location is coolant and water circuits, battery enclosures, transmission assembly, engine assemblies. You've also on the HVAC side, the residential and commercial HVAC systems. You know, a lot of times before the manufacturer fills it with refrigerant, they're going to fill it with a tracer gas and look for a leak in that refrigerant system. So water coils, manifolds, compressors, compressor assemblies. On the refrigerator, on the appliance side of things, you've got commercial, residential, you got the ice and water circuits, you've got the sealed systems, but you've also got vending, on-demand hot water heaters, deep freeze, walk-in coolers, supermarket coolers, and you've also got ice machines, gas dryers, and stoves. And then on the industrial side, cylinders, valves, water valves, hoses, welded stainless pipes, and corrugated tubing. These are all perfect. Applications for open air sniffing. You know, and this, a lot of times people do open air sniffing when it's not, you know, for one, if you're on a very tight budget, but you need the sensitivity of tracer gas. That's why you might pick leak location over one of the other technologies I'm going to go through here in just a second, because it's a very economical way of doing trace gas leak testing with either forming gas or with helium.
Awesome.
So the nitrogen purge system. So you can see a picture of a nitrogen purge stand off to the right, and you see a clamshell with a nitrogen purge built into it to the left. You know, the nice thing about this, it's high resolution, it's low cost. It definitely helps you control your background. So if you're doing open air sniffing, background is always a concern. When you have a clamshell and you put that clamp around a joint or around an area of the part, it doesn't matter if you have an elevated background or not, you're still going to be able to test, because what we're doing is the clamshell itself has a inner purge and an outer purge. The inner purge comes on at the beginning of the cycle when you're evacuating your part and pushes all that contaminated air that's inside that clamshell out. And then you've got a very, you get your outer purge ring, which is a very low pressure of nitrogen that keeps that background from going back into that inner purge. So it's like putting a mini clean room around the joint or an area of the part that you want to test. So like it says here, purging clamshell clamps over the component around joints, fittings, and reduces the environmental effects that you would see with open air sniffing. It's got a sensitivity level down to 1 × 10⁻⁶. It increases your sensitivity and improves the leak detection accuracy. And it comes in various shapes and sizes, which I'll show you here in a few slides. And for the most part, it's designed for manual operator, although we have put clamshells on the end of a end arm robot tooling as well. So here's kind of an example of where you might use one of those clamps. This is an on-demand hot water heater, and you can see the clamp right here clamped on one of the braze joints where it's going from aluminum to copper. And again, the clamshell has the inner and outer chambers like we talked about, inner and outer purge rings. The chamber allows nitrogen to flow into that inner chamber initially, pushing all the background out. And then the inner chamber will collect. So the sniffer one is connected to the inner chamber inside that clamshell. And so your outer purge ring stays on. The sniffer one continues to draw a sample from that inner purge or that inner chamber, so you can tell if you have a leak around that joint or not. And what it does is effectively reduces the chances of getting false failures or false accepts and false rejects.
And I don't think it's shown there. No, this is probably a better place to show it, but you'd actually, you have a place for the sniffer probe to be inserted into your clamshell to detect the.
Yeah, you see where I'm pointing now? You see that little hole
Yep.
right there in the clamshell?
Yep. Sure do.
That's where the sniffer one would be connected. And then you see these ridges right here around the outer perimeter.
Mm-hmm.
That's your outer chamber purge of nitrogen that keeps any atmosphere from getting back into the inside of that chamber purge, and then back into the inner chamber. And you see right here, you've got another hole. That's where we actually push nitrogen into that inner chamber. So the only time the inner chamber purge is on is during initial purge. Once we get below our reject point, we cut off the inner purge. We leave the outer purge ring on, and then we go ahead and backfill the part with trace gas. So you can see the thing. You can see one with the end arm robot tooling that I've got my mouse on. You can see some handheld ones right here, and then you can see another type clamshell right here, another handheld one, like a very basic one. Then you step up to ones that are a little bit fancier. Then you've got one right here that's that goes on the end of a robot. So again, you get your outer purge, your inner purge, and then your sample from the inner chamber. Is that pretty clear, Chris, on how that works?
Very good. Yeah, I think I guess a point to make is when you do use
Sure.
the nitrogen on the inner purge, that's almost the same thing that you just showed, only using a vacuum pump, where you're evacuating the atmosphere out of the part so that the helium or the forming gas can homogenize inside the part. You're using the nitrogen to push atmosphere out so that we get a good clean signal.
Yeah, just so the inner purge just pushes the nitrogen out that would be coming out of this. Nitrogen would be coming in here, is pushing any atmosphere here out into the outer purge ring, and the outer purge ring is designed to blow outward, not inward. So it would pull that contaminated air and push it right back to the outside. Therefore, it wouldn't allow any ingress to get back up into the clamshell from any of the different sides.
Yep. Yeah, this is awesome technology. I like that design.
Yeah, and here's the latest and greatest design of those clamshells right here. They're a lot smaller than the ones that you saw on the previous slide. And what these are good for, it's good for HVAC systems, for for cars, trucks, you know, where you got the braze joints, fuel nuts, anything that you have a joint that you can go around that's that you're trying to leak test with trace gas, purging clamshell is ideal for that. On the HVAC side of things, residential and commercial HVAC systems, where you've got your, again, where you've got your braze joints coming together, getting brazed together or coupled together. Clamshell can clamp right around those, and you can effectively have multiple clamshells on multiple joints and actually test those at the same time, or you can go through and sample each one of those clamshells individually if you want. And then when you get over on the appliance side, like your refrigerator, you've got your sealed side, the back side of the refrigerator where you've got your compressor going over the evaporator and all that. You can clamp the clamshells on those. And then a lot of your on-demand hot water heaters, deep freezers, walk-in coolers, things of that nature are going to have coils that are brazed in, or just the ends of the coils themselves. You can place the clamps around those and essentially do the same thing. Cylinders, refrigerant valves, hoses, welded pipes, corrugated tubing. I think we did an interesting one a while back with a clamshell where we actually had a roll of corrugated tubing that was used in the natural gas industry that we basically did a reel-to-reel. We actually took the hose off of one reel and passed it through the clamshell over onto another reel, so we could actually pull that corrugated tubing through the clamshell and actually identify where a leak was at on that in that roll of corrugated tubing, which was pretty nice.
That was, yeah. I remember seeing that video. It was pretty cool.
Yep. So now we're going to get into trace gas accumulation. I know we're hitting this at a very, very high level. If Russ would want to come back and spend some time on each one of these technologies later on in a seminar where we can go do an in-depth, you know, for people that may be interested in a leak location, purging clamshell, accumulation, or hard vacuum, we can do that. But like I said, we're just kind of doing a 90,000 foot view, kind of showing you what the differences between the different technologies are. This one here, we've got an accumulation. As you can see off to the right here, we've got a plexiglass accumulation hood. You would load the part down into the into the fixture, close the lid, and then what's going to happen is we're going to kind of do the same thing that we did with purging clamshell and leak location. We're going to start to pull vacuum on that part. The same time as we're pulling vacuum on that part, we're also cleaning up the environment on the inside of this chamber here. In this case, it's a Lexan chamber. So we're going to be pumping fresh air in one side and then pulling it out the other side. So that's to get all the contaminated air in there that's inside the chamber where it's contaminated. We're trying to get that environment down below our reject point. Once we get that down below our reject point, we will stop flowing air through the enclosure. We'll stop pulling vacuum on the part, and then backfill the part with trace gas. And in here, what you're going to have is some fans located around on the inside of this chamber. So when we do fill the part with helium, you get a sniffer probe that's coming into the back of the chamber here that's sampling what's going on the inside of that enclosure. And what the four fans are for inside that enclosure is to create a little bit of turbulence, a little bit of air movement around the part. So if I have a leak over here and my sniffer probe is back here, those fans are going to create a turbulence around the part, and it's actually going to push that sample of tracer gas that might be leaking out of the part past that sniffer probe so it can pull it back in. So again, those fans are just mixing the air up inside. And if you do have a leak, it's pushing that sample back past that sniffer probe so that sniffer probe can pick up the leak, the trace gas that's actually leaking out of the part. Is that clear, Chris?
Yeah, that's very good. I like the fact that that's a clear chamber. It makes it a lot easier to see. That's nice.
Yeah, so with that, you can make accumulation chambers out of sheet metal with plexiglass. I just like plexiglass because I can see what's going on. And it's also a relatively inexpensive chamber to put together too with some, you know, some Bosch type 80/20 frame, and it makes for really expensive, very easy to construct, you know, plexiglass chamber. Or like I said, if you want something that looks more durable, you could use a, you know, sheet metal. That's something else you could use. So here's kind of the.
Sorry, Jeff, just a quick question. How important
Sure.
is the seal on, in that case of the chamber you just showed us, it's a hood that you, or a lid that you close, but how
It's a good
important is
question.
the seal?
It's a good question. You want the chamber to be sealed up. So like where you'd put your plexiglass and all that kind of stuff in with the 80/20 frame, I would probably, around all the joints on the inside of that that chamber, I'd probably put like a bead of silicone around to kind of seal up all those openings. And then when you bring the lid down, you could bring the lid down on something like a urethane seal, like a piece of weather stripping, something like that, just to kind of create that seal when the lid closes on the top of the chamber. That completes the seal. But you want it sealed up. I mean, again, the chamber doesn't have to hold up to any type of pressure or any type of vacuum. It's just atmospheric pressure. But like I said, when you put one of those together, just take a thing of silicone, you silicone up all the other joints where the plexiglass would meet the aluminum. And then for the top seal where the lid closes, that could be something as simple as just a urethane seal around, or you know, nothing more than just weather stripping.
Okay. Yeah, that makes a lot of sense.
Yeah, so it's very, very easy to construct a, and then nice thing about it, you can just drop the tooling down into it. You can pull the tooling out. It makes it really easy for if you're testing like multiple different shaped parts inside an accumulation chamber like that, to have the like a subplate. You can just drop down into the chamber and take it out if you want to test something different. So what you have here is this is emulating the sniffer hood. So then your part would be in here under test. You would have your evacuation pump, and you would have your helium supplies. So this is where the TraceMate product would come into play. It would be kind of managing all this right here. But first, we're going to open the valve. We're going to be pulling vacuum on the part. Here, we're going to be circulating air through the chamber right here. Of course, you got your little mixing fans on the inside. And what happens is once our background gets down below a certain level, then we're going to open up the valve here to the mass spec and introduce the mass spec into that chamber, because this is a continuous recirculating loop right here. And the leak detector is going to sample what comes back through this loop out of the chamber. Of course, you got your backing pump there to back up your mass spec. But this is the same sniffer one that you're using on a leak location that you're using on the purging clamshell. You're also using that same sniffer one on the helium accumulation system as well.
That makes sense.
Yep. So here's kind of a sequence of operation. I'm not going to go through this in too much detail, but you know, you seal your chamber from the atmospheric pressure, pull vacuum on the part. The mass spectrometer is open to the chamber, and once it's below the minimum helium set point, we'll do a gross leak check with just maybe a little bit of pressure. And once it's cleaned up, we'll go ahead and fill it to full pressure, do the fine leak test, and then over X amount of time, it's going to come back, give us a pass or fail. Then at the very end, we're going to isolate the mass spec again, and we're going to vent the chamber. We're going to also vent the part, and we're also going to re-evacuate the part. So it's got much like the same sequence as the purging clamshell. You're cleaning up the chamber, you're evacuating the part. Once the part is down below vacuum, once the chamber is clean, down below the reject set point, then we cut off the, we're not circulating any fresh air through the chamber anymore. We're just sitting there allowing the leak detector to draw a sample out of the chamber, and at that point the part's filled. And at the very end, pass fail, we dump the gas out of the part, re-evacuate it. We also, you know, run some fresh air through and clean the chamber back up to kind of prep us for that next production cycle. And here's some examples of some more examples of an accumulation type chamber. This system right here was a CO2 accumulation chamber where we're looking for several cc's a minute. So in this case, it wasn't forming gas, it wasn't helium, it was CO2 that we were using as our trace gas. And so we laid the part on this. This was a wheel rim for a car. So you laid on that lower plate. The plate goes up into the top plate, and it's performing the same accumulation cycle as we talked about in the previous slide. You've got an accumulation chamber right here. This was actually leak testing a sleeve that gets pressed into a big locomotive engine head. And then here, this was a coffin style accumulation chamber. This was for a pretty large radiator. I think the leak rate on this guy was like 5 cc's a minute. And then here you can see another chamber where this one we can actually see the fans inside the chamber. We can also see the inlet and the outer outlet as far as it's doing the recirculation loop, and then your fans that are creating the turbulence. And you can see a couple CTS connects here where you would actually load the part right over the opening of the part right over top of that connector before that door closes.
And I'll just mention, these are all systems that were designed and built at CTS.
That's correct.
Yep.
So with an accumulation system, you can get as cheap and as simple as you want to get to something more exotic, like you see here in some of the other pictures. It really depends on what your budget is and what you're willing to spend. And what this is good for. It's good for when you get in some pressure decay applications where it's not conducive to do a pressure decay type test. It's a really large part, but it's got a fairly liberal leak rate. That's always a good application for an accumulation where pressure decay and mass flow don't fit. Or if I've got maybe a smaller part that's got a really low leak rate that's below the capability of pressure decay, like say 0.01 cc's and below, that's a perfect accumulation test as well. And it's also a good replacement for a dunk tank. Yep. Instead of using a dunk tank, you could use open air sniffing, or you could use accumulation.
We also had an application, Jeff, you may remember, where they were using pressure decay, but whenever you pressure the part, there are internal components that would move under pressure, and took several minutes for them to stabilize. So instead of pressurizing the part and measuring a pressure decay or pressure loss, we switched to this type of test, an accumulation test that worked out great, a lot shorter time.
Right, exactly. And it's like Chris said, on parts of the balloon that are problematic for doing pressure decay. Here we're not measuring a pressure change. All we're measuring is a concentration of gas that leaks out of that part into that chamber. So if you have a part that expands and it's really bad for pressure decay, mass flow, accumulation is a great way to go. Yeah. Or if you've got a really small part with a leak rate that's below pressure decay, but not quite to the point where you'd want to use like a clamshell or something like that, that's good for accumulation as well. So next we've got a hard vac system here. You can see the hard vacuum system off to the side. I will show you a diagram layout of the hard vac system here in just a little bit, but these are your part evacuation pumps, your backing pumps. This is your test chamber right here where you place your part inside. This is your tracer 2 that kind of controls the whole sequence of the whole machine, the evac and fill, as well as the evacuation of the chamber itself. This is the most sensitive test method you can get. You can find stuff all the way down into the -8 cc per minute range and below. Typically the sweet spot for hard vacuums between 1 × 10⁻⁴ and the 1 × 10⁻⁸. I would say most of your applications are going to fall probably within the -5, -6 range. And just for a reference, a 1 times 10 to the minus 5 atmospheric leak cc's per second is equal to 1 bubble underwater release in 25 minutes. All right, here is the layout of the hard vacuum system itself. So again, you've got your charged pneumatics off here on the side where you're pulling vacuum on the part. Here you're actually pulling vacuum on the chamber itself. So you get the part inside the chamber. And this chamber is made out of stainless steel, polished stainless steel. And the reason you can't use like a sheet metal or a plexiglass or something like that, with pulling hard vacuum on this chamber, you would collapse that chamber in a heartbeat. So it's got to be rigid, stainless chamber to be able to do a hard vacuum test. And so what you're doing is you're pulling vacuum on the chamber itself. You're also pulling vacuum on the part itself. Once you get the chamber vacuum down below, let's say 150 millitorr, 150 microns, we'll actually open up the test valve here and introduce the mass spectrometer into the system so we can actually measure any leakage of the helium coming out of that part into the chamber. Will get pulled back into the mass spec, and that will give you your pass-fail reading, where we're actually converting a concentration of that tracer gas, which is measured millivolts. We'll convert that into a leak rate. So here you've got your blower and your pump that's pumping the chamber down really quick, and then once it gets down to the evacuation set point, we open up the valve to the mass spec, introduce that into the system, and then once the background itself is down below the reject set point, we will actually backfill. We'll actually backfill the part with helium back through this circuit right here. And at the very end of the cycle, once we're done, once we make a pass-fail, we will vent the part. The slide I'm on right now, I'm showing the picture of a hard vac system where we've got our hard vac chamber part inside the chamber. We've got our charged pneumatics off to the right there where you see our part evac pump and our helium supply. And then down below, we've got our roots blower, our chamber vacuum pump, and our mass spectrometer. So the way this would work is we would start to pull vacuum with the vacuum pump right here, with the part evac pump. We would also start to pull vacuum on the chamber itself with the roots blower and the chamber pump. Once the chamber is down below 150 millitorr or 200 millitorr in some cases, we would introduce the mass spectrometer to the chamber. Mass spectrometer would start sampling the tracer gas background on the inside of the chamber around the part. Once it's determined we're below our reject point, we will go ahead and open the close the evacuation valve, open up the helium fill valve, charge the part with helium, and then look for a helium leakage out of that part over X amount of time that sample to be pulled back into the mass spectrometer to where we can make a determine accept or reject. So we're basically counting molecules that leak, helium molecules that leak out of the part out into the chamber, and that's being pulled back in. It's being measured by the mass spectrometer. And that's basically converting a millivolt reading into an actual leak rate. So that's kind of a simplified version of the hard vacuum test schematic.
Great.
And in here, this is just kind of showing a graphic of what I just talked about as far as the actual sequence of events. You know, pull vacuum on the part, pull vacuum on the chamber. Once the chamber is at a certain level, 150 microns, 200 microns, we open up to the mass spec to the chamber, make sure the background is down below our reject set point. If it is, we open up the helium fill valve, charge the part with helium, look for helium, rise in helium out of that part into the chamber, and with mass spec sampling over X amount of time. If it passes or it fails, then that will end the test. At the very end of the test, we vent the part, we re-evacuate the part. We do that to get rid of any residual helium so we're not contaminated for our next production cycle. And we also vent the chamber at that point. And a lot of times we will also push nitrogen back into the chamber as well to get rid of any residual helium that might be lingering from the cycle.
I think it's important to note, you'll probably cover this right here, to actually evacuate the helium outside of the room, outside of the area where you're testing, even outside of the building, so you don't contaminate the area.
That's a good point. With all the 4 different technologies I've talked about so far, with any of those technologies, when you go to dump the helium out of the part, you want to dump it out of the building. So it doesn't matter which trace gas technology you're using, you always want to vent the part out the building. And some of the things we take into consideration, we look at cycle time and testing multiple parts is, do you want a dual chamber configuration? You want a chamber where you can test multiple parts? Do you want you want to share components, like share a vacuum pump or a leak detector between 2 chambers or not? Those are just things that we look at when you look at a hard vacuum system, as far as, because it is the most expensive test technology that we have, and it's also the most sensitive. So when we're looking at and we design a system, we kind of look at customer's budget, look at throughput, that kind of thing, and that kind of helps us build the system the most economical way we can, based on the leak rate and based on the throughput of production. Chris, that's the last slide I had.
Thank you very much, Jeff McBee, for sharing all of your knowledge. We will welcome you to come back and take a deeper dive into these technologies. And thank you to all of our customers out there. If it weren't for you, we wouldn't be here. We want to continue to try to give you the knowledge and the tools to become better at what you do. And we look forward to helping you improve all of your processes and your productivity. We would like and welcome you to join us each week, every Wednesday at 11:30 for IndustryCast. And feel free to reach out to us if there's any topics that you'd like to learn about. If there's any feedback that you have for us, we welcome that. You can email us at sales@capexsales.com. And once again, thank you very much. Have a great day.